Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And we're in a little mini series on one-way fixed effects ANOVA. Initially, there were 10 parts, and then I decided to add another part that I'm going to call Residuals. And I had to make the decision, do I change all the previous videos from 10 parts to 11? So this could be 11 of 11. Or do I just call it part 11 of 10? And I decided the latter. Now, as a reminder, the model is y equals x beta plus epsilon. And that can be decomposed into the mu times a vector of 1's, x tau, and then the tau vector. And so these are associated with the fixed effects treatment and plus an error term. The errors are assumed to be normally distributed, mean 0, constant variance, sigma squared. The covariances are 0. Scalar form, it's yij is equal to mu plus tau I, which is the ith treatment effect, plus epsilon ij. Now, I goes from 1 to a, j goes from 1 to n. Epsilon ij's are normally distributed, 0 sigma squared. Epsilon ij's are uncorrelated. Now, the fitted model we call y hat, and it's x times the least squares estimate of beta, which we call beta tilde, because in this setting up here, the design matrix is not a full rank, and the least squares estimate, we have to use what's called a generalized inverse. So this x is here, the least squares estimate of the beta is x transpose x, generalized inverse, x transpose y. Now this first part makes, we call M, which is a perpendicular projection matrix on a column space of x, and then M times y is unique, and we call that the treatment mean vector. And so the structure of this we covered in previous videos. Now from a scalar point of view, the fitted model, so yij hat, is equal to just the ith treatment mean. Now we're going to look at the properties of the residuals. And first we're going to do it in matrix notation, then we'll do it in scalar notation. So we let E, the vector E, be the y values minus their respective fitted values. And then, we hope that these match exactly, but of course they don't. There's fluctuations about this linear model, and those are the errors, or the residuals. Now here, if we substitute in what x beta tilde is, which is my, then right factor out of y, then the residuals can be represented in matrix form as I minus m. Now the interesting part about this is I minus m is a perpendicular projection matrix under the orthogonal complement space of the column space of x. The expected value of the residuals is you just take the expected value of this, and expected value of y is x beta. But since I minus m projects onto the orthogonal complement space of the column space of x, when you take x times it, it projects it down onto the 0 vector, which is, so that's the expected values of the residuals are 0. Now the variance covariance matrix of E, the vector E, and now we can look at it, oh here it is, right? So the variance of that is you take I minus m out front, and then you transpose it out back, but that's a symmetric, so the transposes itself, and then it's the variance of y. Well, the variance of y is sigma squared I, so that sigma squared can come out front, and then since I minus m is idempotent, we just get I minus m. And so this is it. And in previous videos, we looked at the structure of this, and I think it's important to remind ourselves, because when we look at what happens asymptotically, or as n goes to infinity, what happens. So this is actually, so the sigma squared stay the same, and then this is what we'd call block diagonal with I minus j. But j is a matrix of 1's divided by n. But I write it like this, so you'll see what happens in a second. So we call U an n-dimensional matrix of all ones, in n by n matrix. Now, so that says, note that the residuals are a linear combination of the y's. The y's are normally distributed. So that means the residuals are normally distributed with mean vector 0 and variance covariance matrix sigma squared I minus m. Now what happens asymptotically to the variance covariance matrix if we just look at this form right here, right? So this is sigma squared I minus m, which is this. But in this form, notice this piece right here. As n goes to infinity, this is a matrix of ones, and we're dividing by a bigger and bigger and bigger number. So this goes to 0, which leaves a block diagonal of the identity matrix, which is overall just the identity matrix. So in asymptotically, the variance covariance matrix is sigma squared I. Now, note that how much real estate it took to prove and the distributional properties of in matrix form. It's this. Now we're going to do it in scalar form because I think it's informative, but it'll take a little over a page. And so that's one of the big benefits of the matrix version. So the residual in scalar form is EIJ, which is the IJ, response minus its fitted value. And again, we hope the fitted model fits perfectly. But if it doesn't, there's a little difference there, and that's what we call the residual. Now the expected value of EIJ is just the expected value of each of these. Well, this is mu plus tau I. This is a mean, so let's, uncouple it. So let's take the sum, and that's the sum over j divided by how many there are, and they're n, so that's what we get. The expected value goes in, but the expected value is mu plus tau I. And then there's no j, so we get n of these. The n's cancel, and then we get mu plus tau I minus mu plus tau I, which is 0. So the mean is 0. And that's what we set up here. Now the variance of EIJ is we plug in what the EIJ is, which is this. And then this linear combination, so it's the variance of the first plus the variance of the second, and then minus, because that's a minus, 2 times the covariance. Well, this we said was sigma squared. The variance of the mean, the variance operator goes in. Remember that constant that we're dividing by comes out squared. This right here, so we write the sum. That's what this mean, I dot, is this. Sigma squared comes down. This is sigma squared, and then we sum an n of them, so we get n sigma squared. One of the n's cancel, and we're left with this. Now here, the n will come out, the sum comes out front, and we're left with this. But notice that the i's are the same, so we're in the same treatment group, but unless I and j are equal, we're talking about different individuals or different observations, and they're independent. So it's 0. So the only way this is not 0 if j and k equals. It has to be the same person. So that brings us to here, right? Everything else comes down. It's the covariance of this, which we said was sigma squared. And then this can be simplified to sigma squared 1 minus 1 over n. Now, the asymptotic variance of EIJ is as n goes to infinity of this goes to 0, and we're left with just sigma squared, which agrees with our previous, the sigma squared down the diagonal of the variance covariance matrix. And so let's look at the covariance between any two residuals. So EIJ, EKL. We replace what EIJ is and EKL is. And now, when you do the covariance, you look at the covariance of this, covariance of this, covariance of this, covariance of that. And that's what I've rewritten here. And then we have to look at it in different cases. So, when I is not equal to K, so I and K are not equal. So that's observations in different treatment groups. So the observations are independent, so the covariance has to be 0. So when I and J are not equal, it's 0. Now let's look at the case when I and K are equal, so we're in the same treatment group, and J and L are equal, so it's the same observation. So we're the covariance of EIJ and EIJ, but that's just the variance of EIJ, and we looked at that here, so that's sigma squared 1 minus 1 over n. The next case is when I is equal to K and J is not equal to L. So we're in this setting. So when this is the case, I and K are equal, but J and L are not. So it's different observations. So that's 0. Here we write out, this comes down. So IJ, and then this is K, but K is equal to I, and J and L are not equal. But when they're not equal, then that covariance is 0. So we can only look at the case where J and L are the same. So we put J and J in both cases. So here we do the same thing. This is the 1 over the sum of the EIJs. But if K and L are equal, so that we call it just I, and then when this L and the index of this are not equal, then it's different observations. So and the covariance is 0, so that the only case that's non-zero is when it's L. So with the covariance of IL, 1 over n YIL. And then the same way here, it's a sum of this, it's a double sum, but if I and K are not equal, then that's 0, so those have to be equal. So that's why the I and the I here are the same. And the double sum over the second index, when that second index are different, it's a different observation, so they're independent, that's 0. And the only cases that it's not is when those are the same, and so that's why we have IM, and it's summed over that second index. The 1 over n and the 1 over n comes out, and that's how we get the 1 over n squared. 0 goes away. This is the 1 over n comes out, and it's sigma squared. Same way, that's sigma squared. And then this is sigma squared. You get n of them. One of the n's cancel, and we're left with this. And then this reduces to this form. And now note that as n goes to infinity, the covariance goes to 0. And so the EIJs are uncorrelated asymptotically. And so we're finished proving the distributional properties. And scalar form, of course, took much longer to prove it, but it ends up being the same. Well, that's all I have. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.